How small can anything really be? Take a single grain of sand, tiny enough to hold between your fingers. Yet inside it are more atoms than there are stars in the entire observable universe. But compared to the true limits of smallness, it's a giant. Atoms are 100,000 times bigger than their own nuclei. Nuclei are billions of times bigger than the Planck length, the smallest unit of distance physics can even describe. Its length is about 1.6 times 10 to the power of minus 35 meters. This is a concrete limit set by the mathematics that governs space and time. Below that scale, our current theories stop giving reliable answers. The gap between a grain of sand and the Planck length is as vast as the gap between you and the edge of the universe. Today, we begin at that boundary and move outward, layer by layer, until we arrive at a single human being. This is episode 1 of 2, The Hidden World Smaller Than Us. In this episode, you will be taken from the theoretical edge of size, where space itself may be grainy and restless, through the realms of modern particle physics, chemistry, and biology. You will meet the entities that make up matter, vibrating possibilities from speculative string theory, the restless quantum vacuum, quarks and electrons, atomic nuclei and electron clouds, molecules and the folded machinery of proteins, and finally DNA and the cells that compose you. Each step will include clear, verifiable numbers and comparisons so you can hold the scale in your mind. We begin at the Planck length because it frames the question we will return to throughout this episode. What does small mean when space itself may be quantized? From there, we will briefly examine speculative proposals, such as the idea that the most fundamental constituents might be one-dimensional strings, only to anchor ourselves in the experimentally established framework known as the Standard Model. You will learn what quarks are, how they combine into protons and neutrons, and why electrons are treated as fundamental in every experiment to date. Next, the narration will move outward to show how those particles assemble into the atomic nucleus and the surrounding electron cloud. I will make precise comparisons. A nucleus occupies roughly 1/10,000th the size of an atom, while the atom's electron cloud extends far beyond, which means an atom is almost entirely empty space. I will explain what that emptiness implies and why it does not contradict solidity. Then we will translate chemistry into biology. You will see how atoms bond into molecules, molecules fold into proteins, and proteins organize into the cellular machinery that powers life. I will describe ribosomes, mitochondria, membranes, and cytoskeletal structures with concise definitions and with the measurements that place them on the map of scale. In the next episode, episode 2, The Giant Universe Beyond Us, we will reverse direction. We will move outward from the human scale to mountains, planets, stars, galaxies, and finally the observable universe itself, confronting the vast structures that dwarf us and the theories that describe them. Stay with me for the first layer of this voyage, the smallest meaningful scales, the particles that persist under experiment, and the biological constructions that bridge atomic simplicity and human complexity. Okay then, let's start today's documentary. The universe operates on a scale so impossibly small that it challenges every assumption you have about reality itself. Scientists have discovered that space and time are not continuous, smooth fabrics as we experience them, but rather exist in discrete, finite chunks. This fundamental limit is known as the Planck length, measuring approximately 1.6 times 10 to the negative 35th meters. To comprehend this scale requires abandoning all familiar reference points. The Planck length represents the smallest possible measurement of distance that has any physical meaning whatsoever. Below this threshold, the very concepts of length, width and duration cease to exist in any recognizable form. Physics itself breaks down completely at this boundary. Consider the mathematical relationship that defines this limit. The Planck length emerges naturally from three of nature's most fundamental constants: the reduced Planck constant, which governs quantum mechanics, the gravitational constant, which controls the warping of spacetime, and the speed of light, which sets the universal speed limit. When these three constants combine in a specific mathematical arrangement, they produce this tiny length scale that appears to represent the granular structure of reality itself. The Planck length functions as nature's ultimate pixel. Just as your computer screen displays images using discrete pixels rather than truly continuous lines, space-time itself appears to be constructed from these incredibly tiny building blocks. Each Planck length represents one unit of this cosmic pixelation, beyond which no smaller subdivision can exist or be measured. The scale defies human comprehension through conventional analogies. If you could somehow magnify a single Planck length until it reached the size of an ordinary grain of sand, then by the same magnification factor, individual atoms would expand to the size of entire galaxies. This comparison reveals the astronomical gap between the Planck scale and even the tiniest objects we can observe directly. Physicist Rana Adhikari at Caltech provides another perspective on this extraordinary scale. According to his calculations, if a space-time pixel were enlarged to match the dimensions of a grain of sand, then atoms themselves would appear as large as complete galactic systems. This mathematical relationship demonstrates that the Planck length exists at a scale so removed from everyday experience that our usual methods of visualization completely fail. The physical significance of this limit extends beyond mere measurement precision. At distances approaching the Planck length, quantum mechanical effects and gravitational effects become equally important and begin to interfere with each other in unprecedented ways. Our current theories of physics, specifically general relativity and quantum mechanics, operate successfully in their respective domains, but become fundamentally incompatible when forced to describe phenomena at the Planck scale. This breakdown occurs because general relativity describes gravity as the curvature of smooth, continuous space-time, while quantum mechanics requires that energy and matter exist in discrete packets or quanta. When attempting to describe gravitational effects at quantum scales, these two frameworks produce contradictory predictions and mathematical inconsistencies that cannot be resolved using existing theoretical tools. The Planck length therefore represents more than just a measurement limit. It marks the boundary where our understanding of physical reality reaches its current terminus. Below this scale, space and time may not exist as we understand these concepts. Instead, the fabric of reality might consist of something entirely different, perhaps existing in states that have no equivalent in our macroscopic experience. Research into quantum gravity suggests several possibilities for what might exist at or below the Planck scale. Some theories propose that space-time itself is woven from more fundamental entities, possibly discrete geometric structures or quantum loops. Other approaches suggest that the familiar three dimensions of space and one dimension of time emerge from higher dimensional structures that operate according to entirely different physical principles. The practical implications of the Planck length extend to experimental physics as well. No conceivable measurement device could ever directly observe distances smaller than the Planck length, not due to technological limitations, but because of fundamental physical principles. Any attempt to probe such small scales would require concentrating enormous amounts of energy into incredibly tiny regions, which would inevitably create black holes that would obscure the very phenomena being studied. This measurement barrier represents a fundamental limit imposed by nature itself, not merely a temporary obstacle awaiting better instruments. The Planck length therefore serves as an absolute horizon for empirical investigation, beyond which direct experimental verification becomes physically impossible regardless of future technological advances. The discovery and understanding of the Planck length has profound implications for cosmology and our understanding of the universe's origins. During the earliest moments following the Big Bang, when the universe was smaller than the Planck length, conventional physics cannot describe what occurred. This period, known as the Planck epoch, remains completely inaccessible to current theoretical frameworks. The concept of discrete spacetime pixels also raises fundamental questions about the nature of motion, causality, and the flow of time itself. If space consists of individual units that cannot be subdivided further, then continuous motion as we understand it may be an illusion created by our limited perspective. Instead, movement through space might occur in discrete jumps from one pixel to the next, similar to how motion appears in digital animations. These implications extend to the very foundations of mathematics and logic as applied to physical reality. The existence of a minimum length scale suggests that the mathematical concept of infinite divisibility, which underlies calculus and much of theoretical physics, may not correspond to any physical reality. Instead, nature appears to enforce a fundamental granularity that prevents infinite subdivision of space and time. The Planck length thus represents both a destination and a departure point in our scientific understanding. It marks the deepest level to which our current theories can penetrate, while simultaneously pointing toward new physics that must exist beyond this threshold. Understanding what lies beneath this fundamental scale represents one of the greatest challenges facing theoretical physics today. This challenge becomes even more intriguing when we consider that the Planck scale may hide structures that are not smaller in the conventional sense, but rather organized according to completely different principles. Some of the most promising theories suggest that rather than finding smaller particles or shorter distances below the Planck length, we might discover vibrating, string-like entities that give rise to all the particles and forces we observe at larger scales. Beyond the Planck length lies one of physics' most audacious proposals. Every particle you know, electrons, photons, quarks, might not exist as points at all. Instead, they could be manifestations of something far more elegant and profound, vibrating strings of pure energy. String theory represents a fundamental reimagining of matter itself. Where conventional physics treats particles as dimensionless points, string theory proposes that these entities are actually one-dimensional objects, infinitesimally thin strands that oscillate with specific frequencies. These strings exist at the Planck scale, measuring approximately 10 to the power of minus 35 meters in length, making them unimaginably smaller than even the smallest subatomic particles we can currently detect. The mathematical framework underlying string theory emerged from attempts to solve a critical problem in modern physics. Scientists have successfully unified three of the four fundamental forces: electromagnetic, weak nuclear, and strong nuclear forces, but gravity remains stubbornly isolated. Einstein's general relativity describes gravity beautifully at large scales, while quantum mechanics governs the microscopic realm with extraordinary precision. Yet these two pillars of physics become mathematically incompatible when applied simultaneously at the Planck scale. String theory offers an elegant solution. Rather than treating particles as points that create infinite energy densities when they interact, strings have finite size and smooth interactions. This mathematical property eliminates the infinities that plague other attempts to quantize gravity. The theory naturally incorporates gravitons, hypothetical particles that carry the gravitational force, as one particular vibrational mode of strings. Consider how this vibrational mechanism operates. Each string can oscillate in multiple distinct patterns, much like how a guitar string produces different musical notes depending on how it vibrates. In string theory, these vibrational modes determine the fundamental properties of particles: their mass, charge, spin, and other quantum characteristics. An electron emerges from one specific oscillation pattern, while a photon results from an entirely different vibrational frequency. The same underlying string, vibrating in its unique resonant mode, manifests as each type of particle we observe. This vibrational principle extends beyond familiar particle. String theory predicts the existence of supersymmetric partners for every known particle, a mathematical symmetry that doubles the particle spectrum. These supersymmetric particles, if they exist, would possess different statistical properties and could potentially explain dark matter, one of cosmology's greatest mysteries. However, despite decades of searching, no supersymmetric particles have been detected experimentally. The theory requires additional spatial dimensions beyond the three we experience daily. Most string theory formulations demand a total of 10 or 11 dimensions, our familiar three spatial dimensions plus time, along with 6 or 7 additional dimensions that remain compactified and hidden from direct observation. These extra dimensions must be curled up so tightly that they remain invisible at accessible energy scales, yet they fundamentally shape how strings vibrate and therefore determine the properties of particles we observe. The compactification of these extra dimensions presents both opportunities and challenges. The precise geometry of these hidden dimensions determines which particles exist and how they interact. Different compactification schemes can produce entirely different sets of particles and forces, leading to what physicists call the landscape problem. String theory appears to allow an enormous number of possible universes with different physical laws. String theory also introduces extended objects beyond one-dimensional strings. Two-dimensional membranes, or branes, can exist in higher dimensions and potentially explain why gravity appears so much weaker than other forces. In some brane world scenarios, gravity can propagate through all dimensions, while other forces remain confined to our three-dimensional space, naturally explaining gravity's relative weakness. The energy scale required to directly test string theory presents a formidable experimental challenge. The natural energy scale of string theory is the Planck energy, approximately 10 to the power of 19 billion electron volts, roughly 10 to the power of 16 times higher than the most powerful particle accelerators humanity has ever constructed. At such energies, individual strings would become distinguishable from point particles, and the extra dimensions might become directly accessible. Despite these experimental limitations, string theory has produced remarkable theoretical insights. The mathematical techniques developed for string theory have found applications throughout physics and mathematics, from nuclear physics to pure mathematics. The theory has also led to profound discoveries about black holes, including precise calculations of black hole entropy that match thermodynamic predictions. String theory suggests that space-time itself emerges from more fundamental string interaction. Rather than strings moving through a pre-existing space-time background, the geometry of space and time might arise as collective phenomena from string dynamics. This holographic principle implies that all information contained within a volume of space can be encoded on its boundary, a concept with profound implications for understanding information, entropy, and the nature of reality itself. The theory's mathematical elegance extends to its treatment of symmetries. String theory naturally incorporates gauge symmetries that govern fundamental forces and reveals deep connections between seemingly unrelated physical phenomena. Dualities in string theory show that apparently different theoretical descriptions can be mathematically equivalent, suggesting that multiple perspectives might describe the same underlying reality. Current research in string theory continues along multiple fronts. Theoretical physicists work to understand the landscape of possible string vacua and develop techniques for calculating observable predictions. Others investigate connections between string theory and condensed matter physics, where string-like phenomena emerge in materials like superconductors and quantum spin liquids. The relationship between string theory and cosmology remains an active area of investigation. Some string theory models provide mechanisms for cosmic inflation, the rapid expansion that occurred in the universe's first moments. String theory might also explain the observed value of dark energy and the accelerating expansion of the universe, though definitive connections remain elusive. String theory represents more than just another model of particle physics. It suggests that the familiar world of point particles, forces, and fields emerges from a deeper level of reality, where everything consists of vibrating strings in higher dimensional space. These tiny, oscillating entities existing at the very limits of meaningful space and time could be the fundamental constituents from which all matter, energy, and even space-time itself arise. Whether string theory ultimately describes our universe remains an open question. The theory's mathematical beauty and theoretical consistency continue to attract physicists, while its experimental inaccessibility generates ongoing debate about its scientific status. Regardless of its ultimate fate, string theory has already transformed our understanding of what fundamental physics might look like and continues to guide theoretical investigations into the deepest levels of reality. From this vibrating foundation of strings, we must ask what these oscillations move through. If strings are the fundamental constituents, what comprises the stage upon which they perform? The next chapter explores quantum foam, the turbulent, ever-changing fabric of spacetime itself at the Planck scale. Empty space is a lie. What you perceive as the vacuum between atoms, the void between stars, the nothingness that fills the universe, none of it actually exists. At the most fundamental level, what we call empty space seethes with activity so violent and chaotic that it defies human comprehension. When we descended to the Planck length in our previous exploration, we encountered the ultimate pixel of space-time itself. But this pixel is not static. It writhes. It bubbles. It creates and destroys matter in cycles measured in the briefest moments imaginable. This is quantum foam, and it represents the true foundation upon which all reality stands. The concept emerged from the brilliant mind of physicist John Wheeler, who recognized that at distances approaching 1.6 times 10 to the power of -35 meters, space-time cannot maintain the smooth fabric that Einstein described in general relativity. Instead, the very geometry of space and time becomes subject to the uncertainty principle of quantum mechanics. The result is a phenomenon so extraordinary that it challenges every intuition we possess about the nature of existence. Consider what quantum field theory reveals about the vacuum of space. According to Heisenberg's uncertainty principle, energy and time cannot both be precisely determined simultaneously. This fundamental limitation of measurement creates a profound consequence. The energy of empty space cannot remain at zero for any measurable duration. Instead, it must fluctuate wildly, borrowing energy from the future and paying it back in intervals so brief that direct detection becomes impossible. These are not mere theoretical abstractions. Virtual particle pairs, matter and antimatter twins, spontaneously materialize throughout the vacuum, existing for fleeting moments before mutual annihilation returns their borrowed energy to the quantum field. An electron and positron flash into existence, dance their brief cosmic ballet, then vanish as if they never existed at all. Photons split into particle pairs, recombine and disappear. Quarks and antiquarks emerge from nothingness only to immediately cancel each other out. The mathematics governing these processes reveal something astounding. This activity occurs everywhere, at every point in space, throughout every moment of time. The vacuum buzzes with the constant creation and destruction of virtual particles at a rate that becomes more intense as we examine smaller and smaller volumes of space. At the Planck scale, this activity reaches such extremes that space-time itself begins to fluctuate. At the Planck length, the energy density of virtual particle creation and annihilation becomes so enormous that it begins to warp space-time according to Einstein's equations. But here lies the crucial problem. General relativity assumes that space-time provides a smooth, continuous stage upon which quantum events unfold. Quantum mechanics, meanwhile, treats space-time as fixed while allowing matter and energy to behave probabilistically. When both theories operate simultaneously at the Planck scale, they produce a contradiction that reveals the limits of our current understanding. The virtual particles created by quantum fluctuations possess energy, and energy curves space-time. But the curved space-time affects the quantum fields that create the virtual particles. This feedback loop creates a situation where the very concept of distance becomes uncertain. Wheeler recognized that if you attempt to measure the length of an object at the Planck scale, the energy required for such measurement would be sufficient to create virtual particles with such intensity that they would gravitationally distort the space-time you are trying to measure. The measurement process itself fundamentally alters the quantity being measured, not merely due to the act of observation, but because the energy required for observation creates new gravitational effects that change the local geometry of space and time. The structure that emerges from these quantum gravitational effects resembles foam on a turbulent sea. Just as ocean foam consists of countless bubbles forming and popping in chaotic patterns, quantum foam represents space-time as a frothy, ever-changing medium, where the normal concepts of distance and duration lose their meaning. Within this foam, space and time do not flow smoothly from point to point. Instead, they form temporary bubbles and connections that appear and disappear according to quantum probabilities. A path between 2 points might twist through higher dimensional spaces, branch into multiple routes, or even reverse direction temporarily before reaching its destination. The topology of space itself becomes dynamic and probabilistic rather than fixed and deterministic. This foam-like structure operates on scales so minute that its effects remain invisible to all current experimental techniques. Even our most sensitive instruments cannot directly probe distances smaller than approximately 10 to the power of minus 18 meters, still 17 orders of magnitude larger than the Planck length where quantum foam dominates. We infer its existence through mathematical consistency requirements and the demand that quantum mechanics and general relativity must somehow unite in a complete theory of quantum gravity. The significance of quantum foam extends far beyond its role as a curious feature of theoretical physics. If this description proves correct, then quantum foam represents the deepest level of physical reality, the foundation beneath all other foundations. Every particle, every force, every structure in the universe emerges as an excitation or pattern within this underlying foam. Consider the implications for our understanding of matter itself. The particles we observe, electrons, quarks, photons, may not be fundamental objects but rather stable patterns of disturbance within the quantum foam, similar to how waves on an ocean surface represent organized motions of the underlying water. The forces between particles could arise from the ways these patterns interact within the foamy medium of space-time. This perspective suggests that the apparent solidity of matter represents a kind of illusion created by our limited sensory capabilities and measurement tools. What we perceive as empty space filled with discrete particles actually consists of a single unified field of quantum activity where the distinction between matter and vacuum becomes meaningless at sufficiently small scales. From this chaotic foundation, the ordered universe we observe somehow emerges. The virtual particles that briefly exist within quantum foam occasionally escape their usual fate of immediate annihilation. In the earliest moments after the Big Bang, when the universe expanded rapidly during cosmic inflation, virtual particle pairs were stretched apart faster than they could find each other for annihilation. These escaped virtual particles became the first real matter in the universe. Even today, quantum foam continues to influence the behavior of space and time in subtle but measurable ways. The Casimir effect, where two conducting plates placed extremely close together experience an attractive force, occurs because the quantum foam between the plates differs from the foam outside them. The restricted space between the plates allows fewer virtual particles to form, creating a pressure difference that pushes the plates together. Hawking radiation from black holes also originates in quantum foam. Near a black hole's event horizon, virtual particle pairs can be separated by the extreme gravitational field. If one member of the pair falls into the black hole while the other escapes, the black hole loses energy equal to the mass of the captured particle, causing the black hole to slowly evaporate over astronomical time period. Quantum foam represents not merely a physical phenomenon but also the fundamental limit of human knowledge about the universe. Below the Planck scale, the concepts of space, time, causation, and existence itself become so intertwined with the act of measurement that objective reality and subjective observation cannot be separated, even in principle. This limitation is not temporary, awaiting more sophisticated instruments or mathematical techniques. It appears to be absolute, built into the logical structure of any possible physical theory that includes both quantum mechanics and general relativity. The foam marks the boundary between the knowable and the unknowable, between the world of phenomena and the deeper reality that lies forever beyond direct observation. Yet this boundary provides its own profound insights. Quantum foam reveals that at its deepest level, the universe operates according to principles of creativity and spontaneity, rather than mere mechanical determinism. The constant creation and destruction of virtual particles suggests that existence itself is fundamentally active and dynamic, rather than passive and static. The universe does not consist of fixed objects moving through empty space according to predetermined laws. Instead, it represents an ongoing process of becoming, where space, time, matter, and energy continuously create themselves through their mutual interactions. We exist not as separate entities within this process, but as temporary patterns of organization that the process creates and sustains. Understanding quantum foam transforms our relationship to existence itself. We are not visitors to a completed universe, but participants in an ongoing act of cosmic creativity that extends from the smallest conceivable scales to the largest structures we can observe. In the next chapter, we will witness how this creative foundation gives rise to the elementary particles that serve as the basic building blocks from which all complex structures emerge. We have descended through the quantum foam and vibrating strings to reach the foundation of spacetime itself. Now we ascend from this chaotic realm to discover something remarkable. Order emerges from chaos. The frenzied quantum vacuum gives birth to stable, well-defined building blocks that form everything you see, touch, and are made of. These are the elementary particles, the true Lego bricks of our universe. The standard model of particle physics represents one of humanity's greatest intellectual achievements. This theory catalogues exactly 61 elementary particles when we count all their flavors, spins, and antiparticles. Think about that for a moment. The entire complexity of our universe, from the device you're watching this on to the furthest galaxy, emerges from just 61 fundamental building blocks. These particles fall into three distinct categories, each playing a crucial role in constructing reality. The first category contains the matter particles, which provide the substance of everything around us. The second category houses the force carriers, which govern how particles interact with each other. The third category contains just one particle, the Higgs boson, which grants mass to all the others. The matter particles divide into two families, quarks and leptons. Understanding this division reveals why some particles can exist freely while others remain forever trapped. The quark family contains 6 members, organized into 3 generations. The first generation includes the up quark and down quark, the most stable and abundant quarks in our universe. These particles carry electric charges that seem strange at first. The up quark carries a charge of positive 2/3, while the down quark carries negative 1/3. These fractional charges initially puzzled physicists, but they serve a crucial purpose in building larger particles. The second generation contains the charm quark and strange quark. These particles rarely appear in everyday matter because they decay rapidly into their lighter cousins. The charm quark carries the same charge as the up quark, while the strange quark matches the down quark's charge. The third generation houses the heaviest quarks, the top quark and bottom quark. The top quark holds the distinction of being the heaviest elementary particle we know, with a mass nearly equivalent to a gold atom. These massive particles exist only briefly in high-energy collisions before decaying into lighter particles. Every quark carries what physicists call color charge, a quantum property entirely unrelated to visible color. This charge comes in 3 types: red, blue, and green. The strong nuclear force carried by gluons acts only on particles with color charge. This creates a fundamental rule: quarks cannot exist in isolation. They must always bind together in combinations that produce colorless composite particles. The lepton family also contains 6 members, but these particles behave very differently from quarks. Leptons carry no color charge, which means they feel no influence from the strong nuclear force. This freedom allows leptons to exist as isolated particles. The first generation of leptons includes the electron and electron neutrino. The electron, with its negative charge and tiny mass, forms the outer shells of atoms and enables all of chemistry. The electron neutrino carries no electric charge and almost no mass, allowing it to pass through ordinary matter as if it weren't there. The second generation contains the muon and muon neutrino. The muon behaves like a heavy electron. It carries the same negative charge but weighs about 200 times more. Like all second and third generation particles, Muons decay rapidly into lighter particles. The third generation houses the tau particle and tau neutrino. The tau particle acts like an even heavier electron, weighing about 3,500 times more than its first-generation cousin. Tau particles decay so quickly that they travel only microscopic distances before transforming into other particles. Each matter particle also has an antimatter counterpart, a particle with opposite charge but identical mass. When matter meets antimatter, both particles annihilate completely, converting their mass into pure energy, according to Einstein's famous equation. The universe operates through four fundamental forces, and three of them arise from the exchange of force-carrying particles called bosons. These invisible messengers create all the pushes and pulls that govern how particles interact. The photon carries the electromagnetic force, the interaction responsible for light, electricity, magnetism, and chemical bonds. Photons have no mass and no electric charge, allowing them to travel at the speed of light indefinitely. Every time you see light, feel warmth from the sun, or use any electronic device, you're experiencing photon exchanges. The electromagnetic force shapes atoms by holding electrons in orbit around nuclei, and it governs all chemical reactions by allowing atoms to share or transfer electrons. The strong nuclear force operates through 8 different particles called gluons. These massless particles carry color charge, making them unique among force carriers. They interact not only with quarks but with each other. This self-interaction creates an unusual phenomenon. The strong force actually grows stronger as particles move farther apart, like stretching a rubber band. This property ensures that quarks remain forever confined within composite particles like protons and neutrons. The weak nuclear force manifests through 3 particles, the W+ boson, W- boson, and Z boson. Unlike photons and gluons, these particles carry significant mass, about 80 to 90 times heavier than a proton. This enormous mass severely limits their range, confining weak interactions to subatomic distances. The weak force governs radioactive decay processes and plays a crucial role in nuclear fusion reactions that power stars. Gravity, the fourth fundamental force, presumably operates through a hypothetical particle called the graviton. However, gravitons have never been detected, and incorporating gravity into the standard model remains one of physics' greatest challenges. The extreme weakness of gravity compared to other forces makes graviton detection extraordinarily difficult with current technology. The Higgs boson stands alone in its own category, serving a unique function that makes all other particles possible. This particle emerged from theoretical work by Peter Higgs and several colleagues in the 1960s, but remained undetected until 2012, when experiments at the Large Hadron Collider finally confirmed its existence. The Higgs boson connects to something called the Higgs field, an invisible energy field that permeates all of space. Unlike electromagnetic or gravitational fields, which vary in strength from place to place, the Higgs field maintains a constant non-zero value throughout the universe. This field fundamentally shapes reality by determining which particles have mass and which remain massless. When particles move through the Higgs field, they interact with it differently. Particles that interact strongly with the field acquire large masses, while particles that barely interact remain nearly massless. Photons don't interact with the Higgs field at all, which explains why light travels at maximum speed and photons have no mass. The discovery of the Higgs boson required building the most powerful particle accelerator ever constructed. The Large Hadron Collider, stretching 27 kilometers around, smashes protons together with tremendous energy. These collisions occasionally produce Higgs bosons, which decay almost instantly into other particles. Scientists identify Higgs bosons by carefully analyzing the debris patterns from millions of collisions. Despite its remarkable success, the Standard Model leaves several profound mysteries unsolved. The theory cannot explain gravity, dark matter, or why neutrinos have mass when the original model predicted they should be massless. It also fails to account for the vast disparity between matter and antimatter in our universe. According to the Standard Model, equal amounts of both should exist. These limitations suggest that the 61 particles represent only a partial picture of reality's foundation. Physicists actively search for signs of additional particles and forces that might complete our understanding. Experiments probe higher and higher energies, seeking evidence of supersymmetric particles, extra dimensions, or entirely new categories of matter. The elementary particles we've discovered transform the ancient philosophical question, what is everything made of, into a precise scientific answer. Every atom in your body, every ray of sunlight, every force that holds you to Earth, all emerge from combinations and interactions of these 61 fundamental entities. They represent the alphabet from which the universe writes its story, from the smallest molecule to the largest galaxy. The Standard Model reveals that beneath the incredible diversity of phenomena we observe lies a profound simplicity. A handful of particles governed by mathematical laws generate the endless complexity and beauty of the natural world. These particles bridge the gap between the quantum foam of space-time and the atoms that compose everything we know, serving as nature's construction kit for building reality itself. Inside every atom lies a concentrated fortress of matter so dense that a teaspoon would weigh millions of tons. This fortress consists of protons and neutrons, particles that measure approximately 1 femtometer across, that's 10 to the power of minus 15 meters. To appreciate this scale, consider that if you could magnify a proton to the size of a soccer ball, an actual soccer ball would expand to roughly the diameter of Earth. These nuclear particles represent the next level in our hierarchical understanding of matter. While we explored elementary particles as fundamental building blocks, protons and neutrons demonstrate how these elementary components combine to create the first stable composite structures in nature. This transition from elementary to composite represents one of the most significant organizational principles governing our physical reality. Protons and neutrons belong to a family called nucleons, and their internal structure reveals the elegant simplicity underlying apparent complexity. Each proton contains precisely 2 up quarks and 1 down quark, bound together by the strong nuclear force mediated by gluons. The up quarks carry a fractional electric charge of positive 2/3 each, while the down quark carries negative 1/3. This arithmetic yields the proton's characteristic positive charge of exactly 1 elementary charge unit. Neutrons follow a complementary pattern with 2 down quarks and 1 up quark. The electrical charges again sum precisely. 2 negative 1/3 charges plus 1 positive 2/3 charge equals 0, giving the neutron its electrical neutrality. This mathematical precision demonstrates how nature achieves stability through balanced charge distributions at the most fundamental level. The strong force that binds these quarks together operates through continuous exchanges of gluons, particles that carry the strong nuclear force. Unlike electromagnetic forces that weaken with distance, the strong force actually increases as quarks attempt to separate. This creates a phenomenon called quark confinement, ensuring that quarks never exist in isolation under normal conditions. The masses of protons and neutrons reveal another fundamental principle of physics. Each proton weighs approximately 938 million electron volts, while neutrons are slightly heavier at 940 million electron volts. However, when we examine the constituent quarks, we discover something remarkable. The quarks themselves contribute only a small fraction of the total nuclear mass. The majority of a proton or neutron's mass actually emerges from the energy of the gluon field that binds the quarks together. Einstein's mass-energy equivalence, E equals mc squared, manifests directly in these particles. The intense energy required to confine quarks within such a tiny volume translates into substantial mass, demonstrating how binding energy becomes an intrinsic component of matter itself. This mass generation through binding energy explains why nuclear physics involves such enormous energies. When nucleons combine to form atomic nuclei, or when they break apart, the changes in binding energy can power stars, nuclear reactors, or unfortunately, nuclear weapons. The energy scales involve dwarf chemical reactions by factors of millions. Both protons and neutrons exhibit quantum mechanical properties that distinguish them from classical objects. They possess intrinsic angular momentum, called spin, with each nucleon carrying exactly 1/2 unit of quantum spin. This quantum property affects how nucleons behave when grouped together in atomic nuclei and influences the magnetic properties of atoms. The neutron presents a particularly fascinating case study in particle physics. Despite carrying no net electric charge, neutrons possess a magnetic moment, indicating that electric charge moves within the particle. This internal charge distribution reflects the motion and arrangement of the constituent quarks, providing experimental evidence for the quark model of nucleon structure. Neutrons also exhibit radioactive decay when isolated from atomic nuclei. A free neutron survives for approximately 15 minutes before transforming into a proton, an electron and an electron anti-neutrino through weak nuclear decay. This instability outside of nuclei highlights the delicate balance of forces required to maintain particle stability. While protons and neutrons form the nuclear core, electrons complete the atomic structure by occupying the space surrounding the nucleus. Electrons belong to the lepton family of elementary particles and carry exactly 1 unit of negative electric charge, perfectly balancing the positive charge of protons in neutral atoms. The electron's mass represents only about 1/1800th that of a proton, yet electrons determine most of an atom's chemical properties. Their arrangement in quantum mechanical orbitals around the nucleus governs how atoms bond with each other, conduct electricity, absorb light, and participate in chemical reactions. Current experimental limits place the electron's size below 10 to the power of -18 meters, making it effectively point-like within our measurement capabilities. This contrasts sharply with protons and neutrons, which have measurable internal structure. The electron appears to be truly elementary, not composed of smaller constituents. The size relationships between atomic nuclei and their components reveal the incredible density of nuclear matter. A typical atomic nucleus measures between 1 and 10 femtometers in diameter, depending on the number of nucleons it contains. Since individual nucleons are roughly 1 femtometer across, nuclei pack these particles with minimal empty space between them. This dense packing creates matter densities that exceed anything encountered in everyday experience. Nuclear matter reaches densities of approximately 2.3 times 10 to the power of 17 kilograms per cubic meter. To put this in perspective, a sugar cube made of nuclear matter would weigh roughly the same as Mount Everest. Such extreme densities exist naturally only in the cores of neutron stars, where gravitational collapse compresses matter beyond the limits that support ordinary atomic structure. Under these conditions, electrons merge with protons to form additional neutrons, creating objects that consist almost entirely of nuclear matter. The formation of stable nucleons represents one of the universe's most crucial organizational transitions. During the first microseconds after the Big Bang, quarks existed freely in a hot, dense plasma. As the universe cooled, the strong force confined quarks into nucleons, creating the building blocks for all future atomic matter. This confinement process established the mass scale for ordinary matter. Since nucleons comprise over 99.9% of atomic mass, the strong force interactions that create nucleons essentially determine the mass of every atom in the periodic table. Without this organizational level, matter as we know it could not exist. The stability of protons particularly deserves attention, as experimental evidence suggests that protons may be absolutely stable particles. The current lower limit on proton lifetime exceeds 10 to the power of 34 years, far longer than the age of the universe. This extraordinary stability ensures that atomic nuclei can persist long enough for complex chemistry and biology to develop. Modern particle physics experiments routinely study nucleon structure by colliding high-energy particles with nucleons and analyzing the debris. These deep inelastic scattering experiments first revealed the existence of quarks within protons and neutrons during the 1960s and 1970s. Contemporary experiments at facilities like the Large Hadron Collider continue to probe nucleon structure with unprecedented precision. These investigations have revealed not only the three primary quarks, but also a sea of virtual quark-antiquark pairs and gluons that constantly appear and disappear within each nucleon. The experimental study of nucleons has also led to the discovery of hundreds of related particles called hadrons, all composed of quarks and gluons. This rich particle spectrum demonstrates the complexity that emerges when the strong force organizes matter at the subatomic level. Protons, neutrons, and electrons work together to create atoms through a precise balance of forces. The strong nuclear force binds nucleons into stable nuclei, while electromagnetic forces attract electrons to the positively charged nucleus and determine atomic dimensions. The number of protons in a nucleus defines the element's identity and chemical properties, while neutrons provide additional nuclear stability without affecting chemical behavior. Electrons arrange themselves in quantum mechanical orbitals that reflect the electromagnetic environment created by the nuclear charge. This three-component architecture, nuclear protons and neutrons plus orbiting electrons, generates the entire periodic table of elements. Each element represents a different balance of these fundamental building blocks, yet all share the same underlying organizational principles that govern atomic structure. Understanding nucleons and electrons as the immediate constituents of atoms prepares us for the next level of organization, where these components combine to create complete atomic systems with their characteristic sizes, properties, and behaviors that define the material world around us. Everything you consider solid, your chair, your phone, even your own body, exists as an elaborate illusion. The foundation of all matter consists of structures so sparse that they challenge our fundamental understanding of physical reality. We arrive at the atomic scale measuring approximately 10 to the negative 10th meters, 1/10 of a nanometer. This dimension represents the boundary where chemistry emerges from pure physics, where the quantum world begins to manifest properties we recognize in our macroscopic experience. Each atom operates as a complete system, containing a nucleus surrounded by electrons. Yet the proportions within this system reveal something extraordinary. The atomic nucleus occupies a space measuring between 10 to the negative 14th and 10 to the negative 15th meters. Meanwhile, the entire atom spans 10 to the negative 10th meters. Consider this ratio carefully. The nucleus contains more than 99% of the atom's mass, yet occupies less than 1/10,000th of its volume. This creates a situation so counterintuitive that most people struggle to accept its reality. To comprehend these proportions, we must scale up dramatically. If we expanded a single atom to match the size of a professional football stadium, the nucleus would appear as nothing more than a marble positioned at the center of the field. The electrons would exist as tiny specks moving somewhere in the upper reaches of the stadium seating. This analogy remains conservative. In many atoms, the proportional difference exceeds even this dramatic comparison. The vast majority of atomic volume contains absolutely nothing. No particles, no structure, no substance of any kind. The mathematical reality proves even more striking than our analogies suggest. When physicists calculate the volume occupied by nuclear matter versus total atomic volume, they discover that over 99.99% of every atom consists of empty space. This emptiness extends throughout all matter. Your hand appears solid, yet it consists of countless atoms, each maintaining this same sparse structure. When you touch a surface, electromagnetic forces between electron clouds create the sensation of contact, but no actual particles ever touch each other. The implications extend far beyond mere curiosity. Every material property we experience, hardness, texture, resistance, emerges from the interactions between these mostly empty atomic structures. The steel in skyscrapers, the diamond in jewelry, the calcium in your bones, all demonstrate their macroscopic properties through the behavior of these hollow atomic shells. While atoms contain mostly emptiness, their nuclei represent matter in its most concentrated form. Nuclear density reaches approximately 230 million tons per cubic centimeter. A sugar cube of nuclear material would weigh more than all humanity combined. This extreme density results from the strong nuclear force, which operates only at distances comparable to nuclear dimensions. Protons and neutrons pack together with no wasted space, creating the most compact arrangements of matter found anywhere in the universe, outside of neutron stars and black holes. The nucleus maintains its integrity through a delicate balance. The strong force binds protons and neutrons together, despite the electromagnetic repulsion between positively charged protons. This balance determines nuclear stability and explains why only certain combinations of protons and neutrons form stable atoms. Electrons do not orbit the nucleus in simple circular paths, as early atomic models suggested. Instead, they exist in probability clouds called orbitals, where quantum mechanics determines their likely locations at any given moment. These electron clouds define the atom's size and chemical properties. Different orbital shapes, spherical s orbitals, dumbbell-shaped p orbitals, more complex d and f orbitals, determine how atoms bond with each other and form molecules. The electrons never actually occupy specific positions. Rather, they exist as waves of probability, appearing in multiple locations simultaneously until measured or observed. This quantum behavior creates the foundation for all chemical bonding and molecular formation. Each element differs by its nuclear composition. Hydrogen contains 1 proton, helium contains 2, carbon contains 6, and so forth. The number of protons, called the atomic number, defines the element's identity and determines its chemical behavior. Neutral atoms contain equal numbers of protons and electrons, balancing positive and negative charges. However, atoms can gain or lose electrons to become ions, creating the charged particles that enable many chemical reactions and biological processes. Different elements exhibit varying atomic radii, though all follow the same basic pattern of nuclear concentration surrounded by electron probability clouds. Larger atoms contain more electrons in outer orbitals, while smaller atoms keep their electrons closer to the nucleus. This atomic structure creates a fundamental paradox in our understanding of matter. Objects appear solid and impenetrable, yet they consist almost entirely of empty space. Two objects cannot occupy the same location not because of physical obstruction, but because of electromagnetic force interactions between their electron clouds. The sensation of touching something results from repulsive forces acting across empty space. Your fingers never actually contact the surface you touch. Electromagnetic fields create the impression of contact while maintaining separation at the atomic level. This principle extends to all physical interactions. When you sit in a chair, electromagnetic forces between your body's atoms and the chair's atoms create the sensation of support. No actual physical contact occurs between the particles involved. At atomic dimensions, quantum mechanics governs all behavior. Electrons cannot exist at arbitrary energy levels. They must occupy specific quantum states with defined energy values. These quantum restrictions explain why atoms absorb and emit light at characteristic wavelengths. The uncertainty principle becomes significant at atomic scales. We cannot simultaneously know both the exact position and momentum of an electron. This fundamental limitation of measurement reflects the wave-like nature of matter at quantum scales. Quantum tunneling allows particles to pass through energy barriers that classical physics would consider impenetrable. This phenomenon enables many nuclear reactions and electronic processes that power modern technology. The mostly empty structure of atoms enables chemical bonding. Electron clouds from different atoms can overlap, sharing or transferring electrons to create molecules. These interactions occur across the empty spaces between atomic nuclei, demonstrating how emptiness facilitates rather than prevents complex chemical structures. The next level of organization emerges when atoms combine through these electromagnetic interactions, creating the molecular world that forms the foundation of chemistry and biology. The empty space within atoms provides the room necessary for these more complex arrangements to develop. Understanding atomic structure reveals the counterintuitive nature of matter itself. What appears solid exists mostly as void, held together by forces acting across emptiness. This realization sets the foundation for comprehending how simple atomic components assemble into the complex molecular machines that enable life itself. Every breath you take contains approximately 21 sextillion molecules. Every drop of water touching your lips holds more individual units than there are stars in the observable universe. Yet these molecular entities, measuring mere billionths of a meter across, orchestrate every biological process that keeps you alive. Understanding molecules requires recognizing a fundamental transformation in how matter behaves. While atoms represent the building blocks of elements, molecules represent the emergence of chemistry itself. When atoms surrender electrons or share them through precise arrangements, entirely new properties manifest that neither constituent atom possessed independently. Consider the formation of a single water molecule. Two hydrogen atoms, each containing one proton and one electron, approach one oxygen atom containing 8 protons and 8 electrons. The oxygen atom exhibits an intense attraction for additional electrons due to its nuclear charge. Through covalent bonding, the hydrogen atoms share their electrons with oxygen, creating a stable triangular structure measuring exactly 0.275 nanometers across. This molecular architecture transforms 3 separate gaseous atoms into the liquid that comprises 60% of your body mass. The hydrogen-oxygen bond angles create a polar molecule with distinct positive and negative regions, enabling water's remarkable properties as a universal solvent. No individual atom possesses this capacity for dissolving other substances, yet their molecular combination creates this essential characteristic. Molecular bonding operates through two primary mechanisms. Covalent bonds form when atoms share electron pairs, creating strong directional connections that determine molecular shape and properties. Ionic bonds occur when atoms transfer electrons completely, generating charged ions that attract through electrostatic forces. These bonding patterns establish the foundation for all chemical reactions occurring within biological systems. Molecular dimensions span extraordinary ranges while maintaining consistent atomic scale foundations. Simple diatomic molecules like oxygen gas measure approximately 0.3 nanometers in length. Medium complexity molecules, such as glucose, contain 24 atoms arranged in specific three-dimensional patterns, measuring roughly 1 nanometer across. Complex biological molecules extend these dimensions dramatically while preserving atomic-level precision. Carbon atoms demonstrate exceptional versatility in molecular construction due to their ability to form 4 stable covalent bonds simultaneously. This tetravalent bonding capacity enables carbon to create linear chains, branched networks, and ring structures that serve as molecular scaffolding for biological systems. Hydrocarbon molecules exploit this carbon flexibility to generate compounds ranging from simple methane with 1 carbon atom to complex polymers containing millions of carbon units. The transition from simple to complex molecules reveals emergent properties that cannot be predicted from individual atomic behavior. Methane burns as a fuel gas, while longer hydrocarbon chains form solid plastics with entirely different mechanical properties. Molecular complexity creates functional diversity through structural variations rather than compositional changes. Living systems depend on 4 classes of biological macromolecules that demonstrate molecular complexity at its most sophisticated level. Proteins represent folded chains of amino acid molecules that create 3-dimensional structures capable of catalyzing specific chemical reactions. Each protein molecule contains hundreds to thousands of amino acid units arranged in precise sequences that determine final molecular architecture. Enzyme proteins function as biological catalysts by providing molecular environments that accelerate chemical reactions by factors of millions or billions. The enzyme carbonic anhydrase, measuring approximately 5 nanometers in diameter, catalyzes the conversion of carbon dioxide and water into bicarbonate ions at rates approaching the theoretical maximum possible for molecular encounters. This catalytic efficiency emerges from precise molecular geometry that positions reactive groups with atomic-level accuracy. Nucleic acid molecules store and transmit genetic information through sequences of 4 different nucleotide bases. Ribonucleic acid molecules fold into complex 3-dimensional structures that regulate gene expression and protein synthesis. These regulatory functions require molecular recognition between specific base sequences that depends on hydrogen bonding patterns determined by atomic-level interactions. Lipid molecules create cellular membranes through self-assembly processes that demonstrate spontaneous molecular organization. Phospholipid molecules contain hydrophilic head groups attached to hydrophobic tail regions, creating amphiphilic structures that automatically arrange into bilayer membranes in aqueous environments. This self-organization occurs through millions of individual molecular interactions that collectively generate stable cellular boundaries. Biological systems achieve remarkable specificity through molecular recognition mechanisms that operate with extraordinary precision. Receptor proteins embedded in cellular membranes recognize specific signaling molecules through complementary molecular shapes that fit together like three-dimensional puzzles. This molecular recognition enables cells to respond selectively to particular chemical signals while ignoring countless other molecules in their environment. Antibody molecules demonstrate molecular recognition at its most refined level. Each antibody contains binding sites that recognize specific molecular features called antigens with precision measured in angstrom units. The human immune system generates billions of different antibody molecules, each capable of recognizing distinct molecular targets through complementary surface interactions. Molecular recognition extends beyond simple binding to include allosteric regulation, where binding of one molecule to a protein changes the protein's shape and affects binding of other molecules at distant sites. This molecular communication enables complex regulatory networks that coordinate cellular metabolism and maintain biological homeostasis. Carbon-based molecules generate virtually unlimited chemical diversity through combinatorial arrangements of molecular building blocks. Organic chemistry identifies millions of distinct molecular compounds, each with unique properties determined by atomic arrangements and bonding patterns. This molecular diversity provides the chemical foundation for all biological processes and technological applications. Pharmaceutical molecules demonstrate targeted molecular design, where specific atomic arrangements create desired biological effects. Drug molecules interact with particular protein targets through precisely engineered molecular complementarity. The development of effective medications requires understanding molecular interactions at atomic resolution to optimize therapeutic activity while minimizing unwanted side effects. Synthetic polymer molecules extend natural molecular principles to create materials with engineered properties. Plastic molecules represent long chains of repeating molecular units that exhibit mechanical properties unavailable in natural materials. These synthetic molecules demonstrate human ability to manipulate molecular architecture for technological applications. Molecules exist in constant motion at temperatures above absolute zero, creating dynamic systems where molecular interactions continuously form and break. This molecular motion enables biological processes by allowing molecules to encounter each other, react, and separate according to thermodynamic principles. Understanding molecular dynamics reveals how static chemical structures generate dynamic biological processes. Adenosine triphosphate molecules serve as universal energy currency in biological systems by storing chemical energy in phosphate bonds that can be released through controlled hydrolysis reactions. ATP molecules transfer energy between different cellular processes through molecular interactions that couple energy-releasing reactions with energy-requiring processes. Molecular motors represent sophisticated biological machines that convert chemical energy into mechanical work through conformational changes in protein molecules. These molecular devices demonstrate how atomic-level interactions can generate macroscopic biological motion through coordinated molecular movements. The molecular world bridges the gap between atomic physics and biological complexity, revealing how simple chemical interactions generate the sophisticated systems that enable life. Understanding molecules provides essential insight into the mechanisms underlying all biological processes, from the simplest metabolic reactions to the most complex cellular behaviors that sustain living systems. Inside every cell in your body exists a molecule so extraordinary that it defies comprehension. This molecule, deoxyribonucleic acid, contains the complete blueprint for creating and maintaining human life. Yet the numbers surrounding DNA will challenge everything you thought you knew about the space within your own body. DNA represents the ultimate achievement in molecular engineering. This double helical structure measures exactly 2.0 nanometers in diameter, a width so narrow that 50,000 DNA molecules could fit side by side across the period at the end of this sentence. The molecule consists of 4 chemical bases: adenine, thymine, cytosine, and guanine. These bases pair in precise combinations, adenine always with thymine, cytosine always with guanine, creating the rungs of the twisted ladder we recognize as the double helix. The human genome contains approximately 3.2 billion of these base pairs. Each base pair represents one unit of genetic information, one letter in the vast instruction manual that determines your eye color, height, susceptibility to diseases, and countless other characteristics. The precision required for this system exceeds that of any human-engineered technology. A single error in copying, just one incorrect base among billions, can alter protein function and potentially cause genetic disorders. The length calculations for DNA reveal numbers that strain human understanding. Within each microscopic cell nucleus, a space measuring only 10 to 20 micrometers across, lies approximately 2 meters of DNA when fully extended. To grasp this achievement in molecular packaging, consider that this represents a compression ratio of roughly 100,000 to 1. Human engineers have never approached this level of efficient storage. The total length of DNA contained within a single human body reaches astronomical proportions. With approximately 37 trillion cells in an adult human body, and each cell containing 2 meters of DNA, the combined length reaches 74 trillion meters. This distance equals roughly 37 billion kilometers, a number that places your genetic material on cosmic scales. These DNA lengths become meaningful only when compared to familiar astronomical distances. The distance from Earth to our Sun measures 150 million kilometers. Your body's total DNA length could span this Earth-Sun distance approximately 247 times. Alternatively, this genetic material could circle Earth's equator 1.8 billion times, or stretch to the Moon and back 96,000 times. The most striking comparison involves our solar system's boundaries. The heliopause, marking the edge of the Sun's influence, lies roughly 18 billion kilometers from Earth. Your DNA could travel this distance twice over and still have material remaining. These comparisons illustrate how the microscopic world contains structures operating at genuinely cosmic scales. The mechanism by which cells pack 2 meters of DNA into a nucleus measuring micrometers represents one of biology's most sophisticated achievements. DNA does not simply coil randomly within the nucleus. Instead, it undergoes multiple levels of organization that would impress any structural engineer. The process begins with DNA wrapping around histone proteins, creating nucleosomes that resemble beads on a string. These nucleosome chains then coil into 30 nanometer chromatin fibers. The chromatin fibers fold repeatedly, forming increasingly condensed structures. During cell division, this organization reaches maximum density as chromosomes become visible under microscopes. This packaging system serves multiple functions beyond space efficiency. Different regions of DNA must become accessible at specific times for gene expression. The packaging allows cells to expose needed genes while keeping others tightly wound and inactive. The system also protects DNA from damage while permitting essential cellular processes like replication and transcription. DNA storage capacity exceeds that of any human-designed system by orders of magnitude. Each base pair stores approximately 2 bits of information. The human genome's 3.2 billion base pairs therefore contain roughly 6.4 billion bits or 800 megabytes of data. However, this comparison understates DNA's true information capacity. Unlike digital storage systems, DNA information exists in three-dimensional space with complex regulatory sequences, epigenetic modifications, and alternative splicing patterns. The effective information content may exceed the simple base pair calculation by factors of 10 or more. Additionally, DNA serves as both storage medium and processor, actively participating in cellular functions rather than passively holding data. The genetic code operates as a universal language shared by virtually all living organisms. The same four bases that encode human genetics also encode the genetics of bacteria, plants, and every other form of life on Earth. This universality suggests that DNA represents an optimal solution to the problem of biological information storage, a solution discovered early in evolution and retained across billions of years. The code's error correction mechanisms rival those found in sophisticated computer systems. DNA polymerases, the enzymes that copy DNA, possess proofreading capabilities that reduce error rates to approximately 1 mistake per billion base pairs. Additional repair systems continuously scan DNA for damage and correct problems before they become permanent mutations. These revelations about DNA force us to reconsider our understanding of scale and space. Your body contains molecular structures that span astronomical distances when uncoiled. The most sophisticated information storage and processing systems exist not in Silicon Valley laboratories, but within the nucleus of every cell in your body. The next time you consider the vastness of space or the complexity of modern technology, remember that you carry within yourself structures that operate at cosmic scales and information densities that surpass human engineering. The hidden world within us proves as vast and complex as the visible universe beyond us. This molecular foundation sets the stage for understanding how DNA's information becomes translated into the proteins and cellular machinery that actually perform life's functions. The code represents only the beginning. Its expression into working biological systems reveals even greater complexity at the nanometer scale. Within every cell of your body operates a manufacturing system more sophisticated than any human factory. These microscopic entities work at scales measured in billionths of meters, yet they possess precision that surpasses our most advanced engineering. Welcome to the realm of proteins and cellular machines. At this precise moment, inside each of your 37 trillion cells, thousands of protein molecules function as biological machines. These structures represent the fundamental workhorses of life, constructed from chains of amino acids that fold into precise three-dimensional architectures. Each protein molecule measures merely 3 to 6 nanometers across, a dimension so minute that you could align 2 million of them within the width of a human hair. The specificity of protein function depends entirely upon shape. Consider this remarkable principle. A protein's amino acid sequence determines its folding pattern, and this folding pattern determines its function. This relationship between structure and function operates with mathematical precision. When amino acids link together in specific sequences, they create molecular machines capable of performing distinct biological tasks. Among the most crucial cellular machines are ribosomes, complex structures that measure approximately 25 to 30 nanometers in diameter. These ribonucleoprotein assemblies function as living factories, translating genetic information from messenger RNA into functional proteins. Each ribosome contains over 50 distinct protein components, working in coordination with ribosomal RNA molecules. The translation process reveals extraordinary molecular choreography. Messenger RNA enters the ribosome carrying coded instructions from DNA. Transfer RNA molecules transport specific amino acids to the ribosome, where they align according to the genetic code. The ribosome catalyzes the formation of peptide bonds between successive amino acids, gradually constructing protein chains that emerge from the ribosome fully formed. This process occurs with remarkable speed and accuracy. A single ribosome can synthesize proteins containing hundreds of amino acids in mere minutes, maintaining error rates below one mistake per 10,000 amino acids incorporated. Multiple ribosomes can simultaneously translate the same messenger RNA molecule, creating polyribosome clusters that amplify protein production. Enzymes represent perhaps the most elegant examples of molecular machines. These protein catalysts accelerate biochemical reactions by factors ranging from millions to quintillions compared to uncatalyzed reactions. They achieve this acceleration through precise molecular recognition and stabilization of reaction intermediates. The mechanism of enzymatic catalysis demonstrates sophisticated molecular engineering. Each enzyme contains an active site, a precisely shaped cavity that binds specific substrate molecules. Upon substrate binding, the enzyme undergoes conformational changes that position reactive groups optimally for chemical transformation. This induced fit mechanism ensures both specificity and catalytic efficiency. Consider the enzyme carbonic anhydrase, which catalyzes the reversible hydration of carbon dioxide to bicarbonate. This enzyme processes over 1 million substrate molecules per second, operating at the theoretical limit of diffusion-controlled reactions. Such efficiency proves essential for physiological processes, including respiration and pH regulation. Beyond catalysis, proteins provide structural frameworks that maintain cellular integrity. Cytoskeletal proteins form dynamic networks that determine cell shape, enable cellular movement, and organize intracellular transport. These structural elements demonstrate remarkable mechanical properties despite their molecular dimensions. Actin filaments measuring 7 nanometers in diameter polymerize into networks that provide mechanical support and enable cellular motility. Myosin motors interact with actin filaments to generate contractile forces, powering everything from muscle contraction to cellular division. Microtubules, composed of tubulin proteins, form hollow cylinders that serve as highways for intracellular transport. The dynamic nature of these structures enables rapid cellular reorganization. Actin filaments assemble and disassemble continuously, allowing cells to modify their shape and migrate through tissues. This dynamic instability requires constant energy expenditure, but provides the flexibility necessary for complex cellular behaviors. Mitochondria represent cellular power plants, converting nutrients into usable energy through sophisticated molecular machinery. These organelles measure approximately 500 to 1,000 nanometers in length and contain multiple protein complexes that execute oxidative phosphorylation. The electron transport chain consists of 4 major protein complexes embedded within the inner mitochondrial membrane. These complexes transfer electrons from nutrient molecules through a series of redox reactions, simultaneously pumping protons across the membrane. This process creates an electrochemical gradient that drives ATP synthesis through the remarkable molecular motor ATP synthase. ATP synthase functions as a rotary engine, utilizing the proton gradient to drive mechanical rotation of its central rotor. This rotation induces conformational changes in the catalytic subunits, enabling the synthesis of ATP from ADP and inorganic phosphate. Each glucose molecule oxidized through this system yields approximately 30 ATP molecules, representing extraordinary efficiency in energy conversion. Cells maintain organization through sophisticated transport systems powered by molecular motors. These protein machines walk along cytoskeletal tracks, carrying cargo throughout the cellular interior. Kinesin and dynein motors traverse microtubule networks, while myosin motors navigate actin filaments. The mechanism of motor protein function reveals intricate molecular mechanics. Each motor contains a motor domain that binds to cytoskeletal filaments and hydrolyzes ATP to generate force. Conformational changes triggered by ATP hydrolysis produce stepping motions that propel the motor along its track. These steps measure only 8 nanometers for kinesin, yet occur hundreds of times per second. The cargo-carrying capacity of these motors enables long-distance intracellular transport. Vesicles containing neurotransmitters travel from neuronal cell bodies to synaptic terminals through kinesin-mediated transport. Organelles redistribute throughout cells during division through coordinated motor activity. This transport system maintains cellular organization across distances that span thousands of times the motor's own dimensions. The transformation of linear amino acid sequences into functional three-dimensional proteins represents one of biology's most remarkable processes. Protein folding occurs through a complex energy landscape where amino acid interactions guide the polypeptide chain toward its native conformation. Molecular chaperones assist this folding process, preventing misfolding and aggregation that could prove toxic to cells. Heat shock proteins bind to partially folded proteins, providing protected environments for proper folding. The GROL-GROES chaperonin system encapsulates individual protein molecules within barrel-shaped chambers, facilitating folding through isolation from cellular crowding. Protein misfolding contributes to numerous diseases, including Alzheimer's disease, Parkinson's disease, and Huntington's disease. These conditions involve the accumulation of misfolded proteins that form toxic aggregates, disrupting cellular function. Understanding protein folding mechanisms provides crucial insights for developing therapeutic interventions. Cells maintain protein quality through sophisticated surveillance and degradation systems. The ubiquitin proteasome pathway identifies damaged or misfolded proteins through molecular tagging and delivers them to proteasome complexes for degradation. Proteasomes function as cellular recycling centers, breaking down tagged proteins into constituent amino acids that can be reused for new protein synthesis. These barrel-shaped complexes contain multiple proteolytic active sites that systematically degrade substrate proteins. The energy requirement for protein degradation reflects the importance of maintaining protein quality within cells. Autophagy provides an additional quality control mechanism, enabling cells to degrade larger structures, including damaged organelles. This process involves the formation of double membrane vesicles called autophagosomes that engulf cellular components and deliver them to lysosomes for degradation. Autophagy becomes particularly important during cellular stress, enabling survival through recycling of cellular resources. The protein machines operating within your cells demonstrate that life functions through sophisticated nanotechnology. These molecular devices exhibit precision, efficiency, and coordination that enable the complex processes sustaining biological existence. From ribosomal protein synthesis to mitochondrial energy production, cellular machines operate continuously at scales invisible to human perception, yet essential for every aspect of biological function. The remarkable properties of these molecular machines emerge from their precise atomic organization. Individual atoms contribute specific chemical properties that combine to create emergent functions impossible at smaller scales. This hierarchical organization, from atoms to molecules to molecular machines to cellular systems, illustrates the fundamental principle that complexity can emerge from simple components through proper organization and coordination. Understanding these molecular machines provides profound insights into the nature of life itself. The transition from inanimate chemistry to living systems occurs through the organization of molecular components into functional networks capable of self-maintenance, reproduction, and evolution. These nanoscale machines represent the fundamental units of biological complexity, bridging the gap between simple chemistry and the magnificent complexity of living organisms. Your existence depends entirely upon the coordinated function of countless molecular machines operating at the nanometer scale. These invisible workers maintain your cellular machinery, synthesize essential molecules, generate energy, and execute the countless processes that sustain life. The next time you consider the nature of biological existence, remember that life itself is nanotechnology in action. At this very moment, 37 trillion microscopic factories operate with precision that surpasses any human engineering achievement. These cellular powerhouses, each measuring merely 10 micrometers across, coordinate complex biochemical operations while maintaining perfect synchronization across your entire organism. Every single cell functions as an autonomous city, complete with specialized districts, transportation networks, power generation facilities, waste management systems, and communication infrastructure. The scope of activity occurring within these microscopic boundaries challenges our understanding of what constitutes complexity at the smallest scales of life. Cells represent the foundational building blocks of all biological existence. These microscopic structures, typically ranging from 10 to the -6 meters to 10 to the -5 meters in diameter, establish the critical threshold between the molecular world we have explored and the macroscopic biology we can observe directly. Consider the extraordinary nature of cellular dimensions. A typical animal cell measures approximately 10 micrometers across, which places it at the exact boundary of human visual perception. These structures remain invisible to the naked eye, yet they contain the complete molecular machinery necessary to sustain life, reproduce, and respond to environmental changes. The mathematical precision of cellular organization becomes apparent when we examine their internal architecture. Each cell maintains a complex three-dimensional organization where thousands of different proteins, millions of lipid molecules, and billions of water molecules coexist in carefully regulated concentrations and spatial arrangements. The 37 trillion cells comprising your body represent hundreds of distinct cellular types, each engineered for specific functions within the larger biological system. Skin cells form protective barriers with specialized junction proteins that create waterproof seals. Neurons extend microscopic cables across meter-long distances to transmit electrical signals throughout your nervous system. Red blood cells sacrifice their internal organelles to maximize oxygen-carrying capacity, creating specialized transport vehicles for respiratory gases. This cellular specialization demonstrates remarkable efficiency principles. Muscle cells pack their internal space with contractile proteins arranged in precise geometric patterns that generate coordinated force production. Immune cells maintain rapid mobility systems and sophisticated recognition mechanisms that allow them to patrol your body and identify foreign threats with extraordinary accuracy. Each cellular type maintains its specialized function while participating in the larger coordinated activities of tissues and organs. This dual requirement creates engineering challenges that cellular systems have solved through millions of years of evolutionary optimization. Individual cells operate as complete ecosystems containing multiple specialized compartments called organelles. These subcellular structures function as the essential infrastructure supporting cellular operations, much like the various districts within a metropolitan area serve different urban functions. The nucleus serves as the cellular command center, housing the complete genetic blueprint encoded within DNA molecules. This central organelle maintains strict access control through nuclear pores that regulate molecular traffic between the nuclear interior and the surrounding cellular environment. Within the nucleus, specialized machinery constantly reads genetic instructions and produces messenger RNA molecules that carry construction plans to protein manufacturing sites throughout the cell. Mitochondria function as the cellular power generation facilities, converting nutrient molecules into usable energy through sophisticated biochemical processes. These remarkable organelles, measuring approximately 500 to 1,000 nanometers in length, contain their own genetic material and reproduce independently within cells. Each mitochondrion operates multiple copies of the cellular respiration machinery, generating approximately 30 ATP energy molecules for every glucose molecule processed through oxidative metabolism. The endoplasmic reticulum creates an extensive membrane network that serves as the cellular manufacturing and transportation system. This organelle exists in two distinct forms: rough endoplasmic reticulum, studded with ribosomes for protein synthesis, and smooth endoplasmic reticulum, specialized for lipid production and calcium storage. Together, these membrane systems process and transport thousands of different molecular products throughout the cellular interior. Within each cell, thousands of different protein machines carry out the essential operations of life with remarkable precision and efficiency. These molecular devices, constructed from precise arrangements of amino acid building blocks, function as enzymes, structural elements, transport systems, and regulatory mechanisms. Ribosomes represent perhaps the most sophisticated molecular machines within cells. These massive ribonucleoprotein complexes, measuring approximately 25 to 30 nanometers across, read genetic instructions encoded in messenger RNA and assemble amino acids into functional proteins. Each ribosome operates as a programmable factory, capable of constructing thousands of different protein products based on the genetic templates it receives. The cellular cytoskeleton provides structural framework and transportation infrastructure through networks of protein filaments. Microtubules, intermediate filaments, and actin filaments create three-dimensional scaffolding that maintains cellular shape while providing tracks for molecular motors that transport cargo throughout the cellular interior. These molecular motors demonstrate engineering principles that exceed current human technology. Kinesin and dynein proteins walk along microtubule tracks carrying cellular cargo with directional precision, while myosin motors generate force production through interactions with actin filaments. These protein machines operate with energy conversion efficiencies approaching theoretical maximum limits. Cellular coordination requires sophisticated communication systems that monitor internal conditions, respond to external signals, and maintain operational synchronization with neighboring cells. These communication networks operate through multiple overlapping mechanisms that ensure appropriate cellular responses to changing conditions. Signal transduction pathways function as cellular information processing systems, converting external chemical signals into specific cellular responses. Receptor proteins embedded in cellular membranes detect molecular signals from other cells, hormones, or environmental changes, then transmit this information through cascades of internal molecular interactions that ultimately modify cellular behavior. Gap junctions create direct communication channels between adjacent cells, allowing rapid exchange of small molecules and electrical signals. These intercellular connections enable coordinated responses across tissues while maintaining individual cellular autonomy for specialized functions. Cellular metabolism encompasses the thousands of interconnected chemical reactions that sustain life within each microscopic compartment. These metabolic networks demonstrate remarkable efficiency and regulation, processing nutrients, generating energy, constructing cellular components, and eliminating waste products through carefully coordinated biochemical pathways. Glycolysis, the citric acid cycle, and electron transport chains work together to extract maximum energy from nutrient molecules. These metabolic pathways have been refined through evolutionary processes to achieve optimal energy conversion while minimizing harmful byproducts that could damage cellular components. Anabolic pathways construct the complex molecules required for cellular growth and reproduction, including proteins, nucleic acids, lipids, and carbohydrates. These biosynthetic processes require precise coordination to ensure that cellular components are produced in appropriate quantities and assembled correctly. The most remarkable aspect of cellular function involves their ability to reproduce while maintaining genetic continuity across generations. Cell division represents one of the most complex biological processes, requiring precise duplication of genetic material, organelles, and cellular components before distribution to daughter cells. DNA replication machinery operates with extraordinary fidelity, copying the entire genetic blueprint while making fewer than one error per billion nucleotides copied. This accuracy ensures that genetic information passes reliably from parent cells to offspring cells, maintaining biological continuity across countless cellular generations. The cell cycle control system regulates progression through cellular reproduction phases, monitoring internal conditions and external signals to ensure that division occurs only under appropriate circumstances. This regulatory network prevents uncontrolled cellular proliferation while ensuring adequate cellular replacement for tissue maintenance and growth. Individual cells integrate their activities to form tissues, organs, and complete organisms through carefully coordinated developmental programs and ongoing physiological regulation. This integration requires that each cell balance its autonomous functions with its responsibilities as a component of larger biological systems. Cellular differentiation processes guide the transformation of generic stem cells into specialized cellular types with specific functions within multicellular organisms. These developmental programs involve precise spatial and temporal regulation of gene expression that creates the cellular diversity necessary for complex biological functions. Tissue organization emerges from cellular interactions that establish appropriate spatial relationships, communication networks, and functional coordination between different cellular types. These multicellular arrangements create emergent properties that exceed the capabilities of individual cells operating independently. The 37 trillion cells within your body represent individual units of life that have organized themselves into the complex biological system that constitutes your existence. Each cell maintains its essential living functions while participating in the larger coordinated activities that sustain consciousness, movement, growth, and reproduction at the scale of the complete organism. From the molecular machinery we explored in previous chapters, these cellular cities emerge as the fundamental units where chemistry transitions into biology, where individual molecules organize into living systems capable of growth, reproduction, and response to environmental challenges. Understanding cellular function provides the foundation for comprehending how microscopic processes scale up to create the tissues and organs that will form the subject of our next exploration. The human body contains approximately 37 trillion individual cells, yet despite this staggering number, these microscopic units do not operate in isolation. Instead, they organize themselves into increasingly complex hierarchical structures that transform billions of identical cellular components into the sophisticated biological machinery we recognize as human anatomy. Understanding this organizational principle requires examining how nature solves one of its most fundamental engineering challenges, coordinating the activities of trillions of independent units to create a single functioning organism. The solution lies in a systematic approach to biological architecture that spans multiple scales of organization. While we have established that cells represent the basic units of life, the transition from cellular to multicellular organization involves a critical concept: specialization. Individual cells abandon their independence and commit to performing specific functions within the larger organism. This specialization process, known as cellular differentiation, creates distinct cell types with unique structural and functional characteristics. Consider the dramatic differences between a neuron and a muscle cell. Both contain identical DNA sequences, yet they express entirely different sets of genes, producing proteins that enable vastly different capabilities. Neurons develop extensive branching networks optimized for electrical signal transmission, while muscle cells accumulate contractile proteins arranged in precise geometric patterns. This functional divergence from a common cellular blueprint represents one of biology's most remarkable achievements. The human body contains over 200 distinct cell types, each optimized for specific tasks. Red blood cells sacrifice their nuclei to maximize oxygen-carrying capacity. Immune cells develop sophisticated recognition systems to distinguish between self and foreign materials. Epithelial cells form barrier structures with specialized junction proteins that control molecular passage between body compartments. When specialized cells aggregate and coordinate their activities, they form tissues. Tissue formation represents the first level of multicellular organization above the individual cell. 4 primary tissue types exist in the human body: epithelial, connective, muscle, and nervous tissue. Epithelial tissues create protective barriers and control substance exchange between different body compartments. These tissues form continuous cellular sheets that line body surfaces and cavities. The cells maintain strong intercellular connections through specialized junction proteins that regulate permeability and maintain structural integrity. Epithelial tissues in the digestive tract, for instance, form selective barriers that allow nutrient absorption while preventing harmful substances from entering the bloodstream. Connective tissues provide structural support and facilitate communication between other tissue types. Unlike epithelial tissues, connective tissues contain substantial extracellular matrix composed of proteins like collagen and elastin. This matrix determines the tissue's mechanical properties. Bone tissue creates rigid structural frameworks through mineralized collagen matrices, while cartilage provides flexible support through specialized protein networks that resist compression. Muscle tissues generate mechanical force through coordinated protein interactions. 3 muscle tissue types exist: skeletal muscle for voluntary movement, cardiac muscle for heart contraction, and smooth muscle for involuntary organ function. Each type exhibits distinct cellular organization and regulatory mechanisms optimized for its specific functional requirements. Nervous tissues process and transmit information through electrochemical signals. Neurons form complex networks that integrate sensory input, process information, and coordinate responses. Supporting glial cells maintain neuronal function and regulate the nervous system environment. Organs represent the next organizational level, combining multiple tissue types into functional units. Each organ integrates different tissues in specific arrangements that enable complex physiological processes impossible at the tissue level alone. The heart exemplifies sophisticated organ construction. Cardiac muscle tissue provides contractile force, while specialized nervous tissue coordinates rhythmic contractions. Connective tissue forms structural support and houses blood vessels that supply the muscle. Epithelial tissue lines the heart chambers and forms the valve structures that direct blood flow. This tissue integration creates a pump capable of circulating blood throughout the entire body for decades without interruption. The brain demonstrates even greater organizational complexity. Neural tissue forms processing networks, while glial tissue provides support and regulation. Blood vessels formed from epithelial and connective tissues create the blood-brain barrier that protects neural function. The resulting organ processes sensory information, generates thoughts, and controls body functions through mechanisms that remain incompletely understood, despite centuries of investigation. Organ size varies dramatically based on functional requirements. The skin, technically the body's largest organ, covers approximately 2 square meters of surface area and weighs roughly 16% of total body weight. In contrast, the pineal gland measures only 8 millimeters in length, yet produces hormones that regulate circadian rhythms throughout the entire organism. Individual organs rarely function in isolation. Instead, they organize into organ systems that coordinate activities across the entire body. These systems represent the highest level of biological organization within individual organisms. The cardiovascular system integrates the heart, blood vessels, and blood to transport materials throughout the body. The respiratory system combines lungs, airways, and respiratory muscles to facilitate gas exchange. The digestive system coordinates multiple organs to break down food and absorb nutrients. Each system performs specialized functions while maintaining constant communication with other systems. This inter-system communication occurs through multiple mechanisms. The nervous system provides rapid electrical signaling between organs. The endocrine system uses chemical messengers called hormones to coordinate long-term physiological changes. The immune system maintains surveillance throughout all tissues while coordinating responses to threats. The progression from cells to tissues to organ systems illustrates a fundamental principle of biological organization. Emergent properties arise at each level of complexity. Tissues exhibit capabilities absent in individual cells. Organs perform functions impossible for isolated tissues. Organ systems enable whole-body coordination that transcends individual organ capabilities. This hierarchical organization also demonstrates remarkable efficiency in biological engineering. Rather than creating entirely new structures at each organizational level, evolution repurposes existing components in novel arrangements. The same basic cellular machinery that powers individual cells also drives tissue function, organ performance, and system coordination. The numerical scales involved in this organization challenge human comprehension. a single drop of blood contains approximately 5 billion red blood cells. The adult human brain contains roughly 86 billion neurons forming trillions of synaptic connections. The digestive system processes tons of food annually while maintaining precise chemical balance. Living tissues and organs differ fundamentally from human-engineered structures through their capacity for self-maintenance and renewal. Most tissues continuously replace their cellular components while maintaining structural and functional integrity. The epidermis completely renews itself approximately every 28 days as new cells migrate from deeper layers to replace shed surface cells. The digestive tract replaces its lining every few days to maintain absorption efficiency despite constant exposure to digestive chemicals. Even bone tissue, seemingly permanent, undergoes continuous remodeling as specialized cells remove old bone matrix while other cells deposit new material. This dynamic architecture requires sophisticated regulatory mechanisms that coordinate cell division, differentiation, and death across all tissues simultaneously. Disruption of these regulatory systems leads to diseases ranging from cancer, where cell division escapes normal controls, to degenerative conditions where tissue renewal fails to match normal wear. The transition from this cellular and tissue complexity to the complete human organism represents the culmination of biological organization at scales we can directly observe. Every human body integrates this hierarchy of structures, from specialized cells through coordinated organ systems, creating the living platform from which we experience and interact with the world. This organizational achievement becomes even more remarkable when considering that every component, from individual proteins through complete organ systems, ultimately derives from the atomic and molecular scales we explored in previous chapters. The carbon atoms in our proteins, the calcium ions in our bones, and the electrical currents in our neurons all trace back to the quantum mechanical processes operating at the deepest levels of physical reality. Measure approximately 1.7 meters from head to toe. This single measurement represents the culmination of our journey through the hidden world of scales smaller than ourselves. Every atom, every molecule, every cell we have explored exists within the boundaries of your physical form. Your body contains precisely 37 trillion cells. Each cell functions as an independent city of molecular machinery. Yet together they coordinate seamlessly to create the experience of being you. The mathematical precision underlying this biological architecture reveals something profound about the organization of matter in our universe. The human body consists of approximately 7 octillion atoms. That number, written in scientific notation, equals 7 times 10 to the 27th power. To comprehend this quantity, consider that if you could count 1 atom per second without stopping, it would require more time than the age of the universe multiplied by 10 billion to count every atom in your body. These atoms distribute across just a few dozen elements from the periodic table. Oxygen comprises 65% of your mass, primarily locked within water molecules. Carbon accounts for 18%, forming the backbone of organic chemistry within your tissues. Hydrogen contributes 10%, while nitrogen adds 3%. The remaining 4% consists of calcium, phosphorus, and trace elements essential for biological function. Each of these atoms originated in the nuclear furnaces of ancient stars. The calcium strengthening your bones formed during supernova explosions billions of years ago. The iron carrying oxygen through your bloodstream was forged in stellar cores under temperatures exceeding 100 million degrees Celsius. You are literally constructed from stellar debris, reorganized by biological processes into conscious matter. Within your 37 trillion cells, biochemical processes occur at rates that dwarf any human-made system. Your liver cells process toxins, synthesize proteins, and regulate metabolism through thousands of simultaneous chemical reactions. Nerve cells transmit electrical signals at speeds reaching 120 meters per second, enabling thought and sensation. Heart muscle cells contract in perfect synchronization, pumping 5 liters of blood through 100,000 kilometers of blood vessels every minute. The energy requirements for maintaining this cellular activity are staggering. Your body consumes approximately 2,000 calories daily, equivalent to the energy content of 24 kilowatt-hours of electricity. This energy powers the molecular machines within each cell, from ribosomes manufacturing proteins to mitochondria generating ATP molecules. Consider the remarkable fact that these cellular processes occur automatically, without conscious direction. Your brain coordinates this biological symphony while simultaneously generating your thoughts, memories, and consciousness. The neurons firing as you process these words represent the same fundamental physics and chemistry operating throughout your entire body. The human form demonstrates how matter organizes across multiple scales to create increasingly complex structures. Quarks combine into protons and neutrons. These particles form atomic nuclei, which attract electrons to create atoms. Atoms bond into molecules, molecules assemble into cellular structures, cells organize into tissues, tissues construct organs, and organs integrate into the complete biological system that is you. This hierarchical organization follows precise mathematical relationships. The diameter of an atom measures approximately 10 to the negative 10th meters. A typical cell spans 10 to the negative 5th meters. Your entire body extends roughly 10 to the 0 meters or 1 meter. Each scale represents an increase of approximately 100,000 times over the previous level. The stability of this hierarchical structure depends on fundamental forces operating at each scale. The strong nuclear force binds quarks within protons and neutrons. Electromagnetic forces hold electrons to nuclei and enable chemical bonding. Weak nuclear forces govern radioactive decay and certain cellular processes. Gravity, though negligible at molecular scales, shapes the overall architecture of your body and determines your relationship to Earth. Your brain contains approximately 86 billion neurons, each connecting to thousands of others through synaptic junctions. This creates a network of roughly 100 trillion synaptic connections, enabling information processing capabilities that exceed current supercomputers in many domains. Each neuron operates as a sophisticated biological machine, integrating electrical and chemical signals to determine whether to fire an action potential. These action potentials travel along axons at precisely timed intervals, creating the neural activity patterns underlying thought, emotion, memory, and consciousness. The information storage capacity of your brain approaches 1 terabyte, encoded in the strength and connectivity patterns of synaptic connections. This biological database contains your memories, learned skills, emotional associations, and the neural programs governing your behavior and personality. Remarkably, this entire information processing system emerged from the same fundamental particles and forces we have explored throughout our journey. The thoughts occurring in your mind, as you listen to these words, result from quantum mechanical interactions between electrons, protons, and neutrons, organized into the complex molecular machinery of neurons. Your body exists as a temporary arrangement of matter borrowed from the environment. Every 7 years, most of the atoms composing your tissues are replaced through metabolic processes. The carbon atoms in your muscles today may have been part of atmospheric carbon dioxide last year. The water molecules in your cells likely fell as rain within recent months. Despite this constant atomic turnover, biological processes maintain the structural patterns that define your identity. DNA molecules in each cell nucleus preserve the genetic instructions governing cellular function. Protein synthesis machinery continuously replaces worn molecular components. Cellular repair mechanisms correct damage and maintain tissue integrity. This dynamic equilibrium between molecular turnover and structural stability represents one of the most remarkable achievements of biological organization. Your body maintains its essential form and function while existing in constant flux at the molecular level. The journey from the Planck length to human scale encompasses 35 orders of magnitude. If we represented this range linearly, with the Planck length equal to 1 millimeter, a human being would extend across a distance of 100 trillion kilometers. This distance exceeds the diameter of the observable universe by a factor of 1 billion. This comparison reveals the extraordinary position humans occupy in the hierarchy of natural scales. We exist roughly halfway between the smallest meaningful lengths in physics and the largest structures in the cosmos. Our size enables us to manipulate individual atoms through advanced technology while simultaneously observing distant galaxies through telescopes. The matter composing your body has existed since the Big Bang, cycling through countless forms over 13.8 billion years before organizing into the complex biological system, reading these words. The hydrogen atoms in your cells formed during the first few minutes after the universe began. Heavier elements were synthesized in stellar cores and distributed through space by supernova explosions. Your consciousness represents the universe becoming aware of itself through biological processes. The neurons generating your thoughts and the atoms enabling those neurons to function are all part of the same cosmic material, temporarily organized into a form capable of contemplating its own existence. This perspective transforms our understanding of human significance. Rather than occupying an insignificant position in a vast cosmos, we represent a critical scale where matter achieves sufficient complexity to generate consciousness and scientific understanding. Through human observation and reasoning, the universe studies its own fundamental nature. The hidden world smaller than us provides the foundation for everything we experience at human scale. Every sensation, thought and emotion emerges from the coordinated activity of molecular machines operating according to the same physical laws governing quarks, atoms and quantum fields. Understanding these connections between scales reveals the profound unity underlying apparent diversity in natural phenomena. The same electromagnetic forces that bind electrons to atomic nuclei enable neural communication in your brain. The same quantum mechanical principles that govern particle behavior determine the chemical reactions powering your metabolism. Your existence represents the culmination of 13.8 billion years of cosmic evolution. From the initial organization of matter and energy after the Big Bang to the development of biological complexity sufficient to support consciousness. You are simultaneously a collection of fundamental particles and a universe contemplating its own existence through the remarkable phenomenon of human awareness.